My name is ALWANI, and this presentation summarizes the research I conducted through the NSF OREU program at Texas A&M University. This summer, I worked on simulating the B2, B19 phase transformation in NITIF shape memory alloys using molecular dynamics and lamps. These alloys have the ability to remember and recover their shape through the solid-state transformations, which make them ideal for applications in aerospace, biomedical devices, and robotics. However, the reliability of these effects decrease over time due to internal damage that accumulate at the atomic level. My project focuses on investigating how these transformations occur under different loading conditions, thermal, mechanical, and cyclic, and how microstructural features like precipitates influence behavior over time. Why study NITIF at the atomic scale? NITIF alloys are considered high-performance shape memory materials due to their high transformation temperatures and recoverable strains. They are used in jet engine components, deployable space structures, and minimally invasive surgical devices. However, these systems degrade over time. Performance losses like increased hysteresis, reduced transformation strain, and functional fatigue are common, and they all stem from what's happening at the atomic level. So rather than relying solely on macro-scale testing, I simulated these materials under molecular dynamics to observe how atoms move, how defects form, and how transformations evolve. This bottom-up approach helps reveal the true origin of material degradation and gives us a roadmap to improve alloy design. My guiding questions. My project was structured around three core questions. First, how does NITIF behave under different loading conditions? Specifically, what happens when we cool it down versus compress it mechanically? Second, when we cycle the material through repeated transformations, what kind of irreversible atomic scale change starts to build up, and how do they contribute to the material's memory? And finally, what roles do precipitates or nanoscale inclusions play in altering this transformation's behavior? These questions allowed me to explore both fundamental science and practical design principles for next-gen smart materials. To investigate these questions, I used LAMPS, a molecular dynamics simulator, and OVTO, a 3D visualization tool specifically designed for atomic scale analysis. The simulation process began with building supercell of NITIF in its B2 phase. Some structures were pure crystalline, others included precipitate atoms, which I introduced by substituting atoms within a defined spherical region. I ran three types of simulations: cooling systems to capture temperature and induce phase transformation, uniaxial compression to simulate stress-induced transformation, and mechanical cyclic loading to reveal memory and fatigue behavior. OVTO was used extensively to visualize phase structure and identify dislocations under the dislocation extraction algorithm. This result is a multi-scale view of transformation and damage ranging from overall stress-strain behavior down to the individual atomic rearrangements. This graph shows the total potential energy of the system as it cools from high to low temperature. The curve starts out flat, representing stable B2 austenite. As the temperature drops below to the Martinistic start temperature, the energy begins to drop sharply. This corresponds to the B2, B19 transformation. That transformation completes at the Martinist finish temperature, where the energy flattens again. On reheating, the reverse transformation begins at AS and completes at AF, which is autonistic start and the autonistic finish. But notice how this path is not the same. The hysteresis loop is a hallmark of shape memory behavior and shows that the path is dependent on thermal history. The ability to extract these transitions temperatures validate my simulation setup and confirm that the model accurately captures real Martinistic behavior. Transformation under the uniaxial compression. Here, I investigated stress-induced transformation by compressing the structure along the z-axis. The stress-strain curve shows three distinct regions: an initial linear elastic zone where the structure is still B2, a wide plateau where the stress remains nearly constant despite increasing strain, this is the transformation zone, and a post-plateau region where the material stiffness again now deforming the Martinist phase. This plateau is critically important. It indicates the strain is being accommodated not by elastic stretching, but by the transformation of austenite into marstenite. This is called pseudoelasticity in action, the core mechanism behind accutation and shape memory alloys. What's exciting is that the simulation matches what we expect from experiments, but it also allows to let us go and further visualize how atoms physically shift and reorganize during transformation. This is where the memory effects really become visible. The top graph shows 3 full cycles of loading and unloading. Each loop's force forms a hysteresis curve, representing energy loss, energy that's not recovered after unloading. But more importantly, the unloading curve doesn't return to its origin. It stops at a finite value. That means the material retains some of its deformation. The bottom graph quantifies this by plotting residual strain after each cycle. The strain increases and then begins to level off, suggesting partial stabilization. But still, permanent shape change is present. This confirms that as the material undergoes repeated use, it accumulates irreversible structure changes, even though it appears to recover. This is a critical insight for applications where shape memory performance must be consistent across many accutation cycles. Tracking dislocations across cycles. To understand why residual strain appears, I use Ovito's DXA tool to extract dislocations from atomic trajectories. At cycle 0, the system is perfect. No dislocations, no lattice defects. After the first cycle, we begin to see dislocation loops forming, especially near regions where transformation is initiated. By cycle 5, there is a dense, tangled network of dislocations running through the structure. These dislocations interfere with reverse transformation and pin the structure in place. That's why the material doesn't recover completely. These defects physically block atomic motion. So what we see here in this is the microscopic origin of the memory effect. Dislocations accumulate and encode a history of past deformation, ultimately leading to fatigue and performance degradation. For the final simulation, I introduced spherical precipitate inclusions into the crystal lattice, shown here as the orange atoms. These represent the second phase particles or local compositional variations commonly found in real alloys. These precipitates distort the surrounding lattice and create local resistance to transformation. On the right, you see a comparison between the stress and strain curve, one for the system with no precipitates, being the solid blue line, and the one with precipitates, being the dashed orange line. The presence of precipitates raises the stress required to initiate transformation and flattens the plateau. This means the transformation is less cooperative. The material needs more energy to reorient in its internal structure. This result demonstrates how microstructural features, even at the nanometer scale, play a major role in determining macroscopic behavior. It also reinforces the need for multi-scale modeling when designing materials for reliability and performance in real-world conditions. My key takeaways. Over the course of this project, I simulated the full transformation behavior of NITIF under thermal and mechanical cycling. I used atomistic simulations to model B2 to B19 transformations. I was able to observe cycle loading, leading to strain memory and irreversible deformation, which I traced back to dislocation evolution. And I showed that including precipitates add mechanical resistance, proving that microstructure is essential to performance. These simulations provide valuable insight into how shape memory alloys behave at the atomic scale. This kind of work supports smart material design, enabling longer-lasting, more efficient devices in all fields. What can be done in the future? Going forward, adding twin boundaries or grains will bring us closer to experimental microstructures. We can also aim to calibrate the model using the DSC or the TEM data. Long term, these atomistic insights can train machine learning models to predict behavior under new conditions. Thank you for your time, and I would like to thank my mentor, Dr. Jean Brack-LeGravrin, in the OREU program for this opportunity.